And I'll be addressing a topic which is interop. I think we had a discussion towards the tail end of the last presentation on the power shelves. So just carrying on the theme and the challenges we have in that arena and the work we have done so far. So to start, we will be talking about what is the real objective on the interop. How did we all, what did we think of? How did we start? And we formed a committee earlier this year, so get into a little bit of detail on that one. And the challenges that I would be addressing in this presentation, and discussion on the solution around that, implementation phase. And really the key step is it needs the participation of the whole community to make it forward, right? Because there are power supply vendors, there are customers, and we need to make sure that everything works together seamlessly, and you can't do that on your own, so we need everybody's agreement to move forward on that one. So if you look at the wiki definition of what is interop, essentially if you look at a power system, we have of course the power supplies, we have the system controller, we have the BBUs, and at the end they all need to work together seamlessly, right, as entirely units. So idea is actually this is more critical, that you should be able to take PSU from a vendor A or mix that with a vendor B and all the pieces together, and there should be a seamless operation. I mean, that is the end goal of this whole exercise, and that's what we're trying to do with this thing. So it started earlier this year when this was a subcommittee. We discussed, we have our monthly meetings, and during those meetings we discussed, okay, so interop is something that we haven't really looked at, and so we formed a subcommittee around that. And the objective was essentially to be able to explore this and see if we can come up with a specification or a test methodology to address this. So that was the goal. So at this point, there is a document which was done by Facebook, which was, I'm referring to it right here, and released in May 2018, earlier this year. And that went into the details of, okay, so what should the different vendors do? What should be an expectation? Again, this is just one document, and we would invite everybody else to look at the document, add to it if you see anything else, and or have a discussion around it so we can get more framework around that. So some of the key things that we looked at were, if you take the two power supplies, even though they will both be, let's say 5 volts, 20 amps, but they are really different. Their current sharing is not the same. The transient behavior is not the same. And when you insert that into the shelf, you may find the tolerances may be different for those power supplies. So and EMC behavior is another thing, right? They may behave different in terms of EMC. So we run into a lot of challenges to that effect. So we we got this document as a starting point. So the reason I show this first is this is what we started off with, and then we meet once a month, and I mean, of course we could use a lot more participants, a lot more ideas. So essentially what we did is we divided that. So I would say Artisan took on the part where we wanted to look at the current, how does the current sharing affect and the dynamic behavior when you do the transients from 10% load, let's say 90% load, and different. So how can we address that part of the puzzle? Then there was a participation of somebody else from the Apple team, and they took on the mechanical part, the tolerance analysis. So I guess we are dividing this into different bits of work, and the object is, at the end of the day, we can have a specification around it and agree on the test methodology and how we move forward with that. So that's how it all started. This is the document, and I encourage you to go to our page and have a look at this and download it, and just to make yourself familiar with this. So when you look at the interop, right, just a little bit of a primer on interop, what are we facing with? We are facing with challenge of current sharing, communication. If you have system, you have a communication signals going from a PSU to the system. Then there is a control functionality, right? There is power turn on, power turn off, alarms. It's a whole lot of stuff that goes on, and mechanical design we talked about. So this is a simplified block diagram of of the system where we have PSU from vendor 1. Oh, you went away from me. Oh, back. Okay, there we are. So we have a PSU from vendor 1, we have a PSU of another vendor. Oh, this is behaving a little bit erratic. Okay. So we have power flowing, of course, between the two. We have a communication and signals going back and forth. So there is a lot going on, and system by itself has its own EMC components. System itself has output bus bar and filtering. Now these are external to the power supplies, and yet what you're expecting is power supply, this power supply and this power supply should work perfectly. Oh, I think it's very sensitive.
You want me to write your slide?
I should be, okay. Let me give it a shot. If not, if it does it again, I'll give it to you.
Yeah, no problem.
Perfect. Thank you, Steve. So what we try to do in this presentation is, addressing everything is beyond the scope. So, we are taking small chunks, putting it all together. We are looking at current sharing and dynamic response. And these are the two key parts of the puzzle when you do PSUs together in a system. Touch it gently, okay? So this worked this time. So, okay, so this is, I'm not going to get into technical details of a power supply operation that is beyond the scope. I just want to touch on a higher level, but just to appreciate the fact, if you take two power supplies, now this shows the high level block diagram of one power supply, shows you the output section. This is the other power supply, and each power supply has a voltage loop and a current share loop. This is from vendor 1, this is from vendor 2. And at the end of the day, this has, just to appreciate the fact that, there's hundreds and thousands of components. And what we expect is they all need to work seamlessly together. We expect the behavior, what is the end result of the voltage loop of this current share compensation, they should, and when we share the current, it should be within a very tight regulation, whatever the spec might be. Okay, good. So just staying on a higher level, you expect, when we talk about the current sharing, there is a dynamic behavior of power supply. You expect the transients, you expect the load change. You go from 10% load to 100% load, just to give you an example. So essentially, there's a 4 modes of classification which we typically look at, which is the dynamic change, the load dynamic change. That's the frequency at which the load is changing, is slower than the current share loop bandwidth, right? Or the opposite, which is the load dynamic change is faster than the current share loop bandwidth. And if you talk about the power supply, there is the voltage loop response that is slower than the slave. Okay, so you hear these, so these are 4 possible. Without getting into detail, when we talk about master and slave, that's a terminology commonly used in the power supply world. The power supply that has the higher voltage has the maximum current. So that's called the master. And and we keep, there is a certain level we maintain. The other one is called the slave, which has slightly lower voltage. So obviously that will carry slightly less current, right? So there's ideally, if you can take the whole operation, you can divide that into 4 possible combinations of operation. So if one can get handle on these things, we believe we can get into a very stable power supply sharing operation. So what we did is, without getting into technical details, we ran, we took different power supplies from different vendors, and we did this study where, in this case, if you look at this operation, when the load dynamic change is slower than the current share loop bandwidth, okay? So the load is changing and it's much slower. So what happens is, if you see the master, the voltage is higher, the current, this is the other this is the output current of the slave, and these are the voltages, right? Higher voltage, higher current. So what happens is, when you do the dynamic response, there is oscillation, but these stabilize, right? So what we observed is, yes, there is some instability, but at the end of the day, if the load change is slower than the current share loop bandwidth, the role reversal happens. Oh, wow. That was, okay, too slow, okay. And it came back, and we came back into the stable operation. if you take this case, now here the things get a little bit crazy, okay? If the dynamic change, if the load is changing at a very fast rate and the current shared loop bandwidth does not have time to settle. Again, a possibility, different people design feedback loop differently, and this happens in a real design. So you could see that the voltage going up, and the voltage will go up to, it's called the capture range, and we will end up in an unstable operation. So again, a third mode of operation, now we are talking about the voltage feedback loop. Again, this causes instability and it settles down. And again, the fourth mode of operation, when the voltage PSU loop is slower, we get an instability, but again, it takes time to settle down. So at the end of the day, what are we causing? We are seeing a role reversal. Master becomes slave, slave becomes master, and there is a lot of oscillation. Instability, which is not good for power supply operation. So the customers don't like that. So these are the things we need to, so my point is just to show us here was, you get these operations and we need to avoid all these instabilities. So at the end of the day, there's a role reversal, power supply can turn on and off and cause a lot of instability. So, those were the few things that just happened because we did the load change faster or the loops weren't designed correctly. But there are many, many other factors besides those that come into picture. And those are, the interface circuit that people design, the capture range of the power supply. The droop is another key thing in a power supply. It's a drop in the lines if you're familiar with the power supply terminology. Remote sense compensation, again, a few of those things, and system resistance that come into play as well. So we need to pay attention to those things as well. So different approaches and set points, and people set power supply output at different places. So again, what you expect is whether you set at 5 volts or 5.2 volts, they should be able to provide almost the same amount of current within 0.1 or 0.2 amp tolerance, which we all agreed upon. So those causes some issues. So what we did all these studies, and in conclusion, I would just talk about some of the key recommendations. The power supply with the output, see, we need to all agree on a common mode of operation. So that's the theme here. You cannot have two different ways of sharing and expect similar results. So again, a common scheme that's used by most power supply vendors is a master-slave mode of operation. So we would recommend everybody follows that. So what happens? So basically, if that happens well, we can have, and idea is to have a common share bus. Power supplies use a common current share bus. So let's say for zero load, it's 0 volts, and for maximum load, it'll be 5 volts. So everybody follows that. So we need to standardize the share bus voltage, the way we do current sharing, and not only that, the level of linearity of the 5 volts. We think it's a straight line, but the linearity does matter, and we need to specify how linear the slope is. And and capture range setting is within how much accuracy on the top range the voltages can vary with respect to one another. So we need to get into those details as well. Finally, again, some recommendations, and these are going towards our contribution to setting forth the specifications for Interop. So we recommend that the current shared bandwidth loop should be 100 to 200 hertz at full load, and the loop margin should be greater than 60 degrees to ensure, when you do this, if you look at the Bode plot and the stability criteria, without getting into those details, that gives you best performance for hot plug, for AC loss and AC return, and hot swap, right? And if we can do one thing, and this is what we have reached agreement with some of the customers, if we can agree that the load dynamic change is slower than the settling time of the current share loop bandwidth. Seems like a lot of words, but if you think about it, if the settling time is slightly more than the load dynamic change, then majority of these issues can be avoided. And we have tested that very, very successfully. And that would get rid of most of the problem we have in current sharing, dynamic load change, settling, hot plug, and most of those things disappear. And again, just re-emphasizing what I just said, this is the 101 of the feedback loop stability criteria, that the voltage loop bandwidth should be sufficient to meet the dynamic load response and sufficient phase margin so that things settle down in a proper fashion. Okay, so we talked about a lot of words. We can put those things in spec, but the real test is at the end of the day, how are we going to validate it? How are we going to test it, right? So, if you can appreciate, there is a multiple amount of test cases. In this case, we do various load changes from, let's say, 10% to 90%, 20 to 80, different input voltages, different line conditions, different load conditions. So typical Interop test report can go up to 1,000 pages if you look at all those test cases. So it's pretty extensive. And we recommend that we do that at there's different design stages. We should do that at the prototype stage when we exit from the factory, and we trim the PSUs at different levels. We can set one PSU from one vendor. Let's say if the range is from 12 to 12.5, one at 12, one at 12.5, vice versa. So we do at maximum min conditions. We run that at high temperature, low temperature under different conditions. So we have an extensive use case, so we need to put that all in spec. And the recommendation is to do that on an ATE. And manual test, you cannot capture all these combinations. And the reason we recommend using this on ATE is then we can standardize it. So all the different vendors can perform the same set of agreed tests with the same set of agreed specifications. And once you do that, I think you will have a pretty much consistent results to compare, and that'll go a long way. So we look at this. The things we should look at is that we talked about the steady state operation, dynamic operation, startup, shutdown, hot swap, fault simulation, temperature effects. I mean, this plays a whole, in the power supply design, the components behave very differently at different temperature extremes. We need to look at the corner cases, roll swaps. So just to say that the ATE will go a long way to address that. So, that's what we have done extensively. And to showcase this, there is a real example of a test case which we performed with 2 different power supplies set at 2 different conditions, and you can see how well they track each other. This is a real live example of an Interop testability. So, okay, so a lot of discussion on we talked about Interop, on dynamic sharing, but to move forward, how do we make this into, so in this committee right now, we have a power supply vendors, and we have customers as well. So I guess we will get together, we will put forth these recommendations, and then we will get an agreement on, current shear circuit, current loop bandwidth, and the recommendations we have, and we will try to put that in a specification. The work on the mechanical is ongoing. Again, that's a very big part. The different the mounting, airflow direction, and if, let's say for example, if a shelf has 6 power supplies, one power supply is not present, how the backflow, back pressure, all these things can play an important part. We need to define all of those things as well moving forward. So we need some help in that arena. Another part that we haven't tackled yet is the digital communications, where everybody does, let's say, pull up, pull down circuit, the alarms on the output, the interfaces. They should all be consistent, and we need to work and put specification around that as well. So that work needs to be done. So moving forward, we need committee agreement to move forward on these things. Plus, we need volunteers to take it to the next step, and people who want to contribute and make it make it a more valid document, right? So that's what we're looking for going forward on this one. And I guess that brings me to the end of the presentation, and essentially what define the key objectives of Interop. And I try to address current sharing and the dynamic response in this presentation that we thought was a key part in sharing the power supplies. Addressed a few solutions, validating of the solutions and an example. And I look forward to your participation so we take it to the next step. Questions? Please.
Thank you. Good morning.
Good morning.
Thank you about you show about the Interop and then the let's say you integrate two different or more PSU suppliers. Okay, thank you. When you basically integrate two or more different levels, suppliers of the PSU, for example, on the rack, do you have, do we consider to recertify, not recertify, but we basically, if we are to deploy the rack somewhere outside, let's say in Europe, do we have to, say, do a compliance test on that?
Yes, there is. See, initially, you can correct me if I'm wrong, Samir. What we do is we do a complete certification of a PSU for everything. Then we put the validation within the rack.
Yes.
So that is from a vendor A because we have done one, but there is combinations of this.
Yeah.
So that's what is done by the customer when they would put their own equipment along with multiple variations and get a certification as well.
So.
Are you going to add anything to that? Or?
No, we do that as well. So
Yeah.
when we do EMI, EMC compliance, we'll put two different vendors in different shelves.
Right.
Mix and match the combinations and do all the testing.
Okay, so that's a second tier outside of the OEM itself, right?
Oh, yeah, absolutely.
Okay, thank you.
Absolutely. Any other questions?
Just to check, is this for 12 volts or are you looking to roll this
This
into
is
48?
12 volts, 48 volts, anything.
Okay.
Essentially, it applies to not only, it's a very good question, it's not only rack type power supplies, it applies to standard power supplies like CRPS or, if there is N plus N system. So it once you have a methodology, it can apply to almost anything.
So will the current shared circuits be shared between the community or is it something?
Oh, yeah, of course.
Yeah.
We want to, the idea is to have a standardized circuits.
Yeah.
We can recommend the circuit so everybody follows the same or similar methodology. Thank you. Any other questions?
And is the document available in our?
Oh,
is
yeah.
the document available in our wiki
Yes.
site?
Yes, yes, it is. Yeah, and along with this document, we have all our previous discussions and all the minutes that are all archived there as well.
Perfect. Thank you.
Anything else? All right, and thank you for your time. Thank you.
Yeah,